In this video, we will be applying differentiation to solve optimization problems, where we either maximize or minimize certain entities given certain constraints. In real life, we are often faced with decisions to optimize certain things. For example, if we are a manufacturer, we want to make sure that the cost is as low as possible or the efficiency of the processes are as high as possible. However, such optimization problems must always be accompanied by physical constraints in order to make any sense. For example, if I want to make an empty cylinder and I want to make it as large as possible, then without any physical constraints, this problem will be nonsensical because theoretically the cylinder can be as large as I could possibly imagine. But if I say that I want to maximize the volume of the cylinder by using a fixed amount of material, then this problem makes sense because the volume of the cylinder cannot become infinitely big now that there is a constraint of fixed materials being used. To solve optimization problems, we must thus always form two equations. The first equation is called the objective equation, which is the equation we want to optimize. Using our earlier example of the cylinder, the objective equation will thus be the volume of the cylinder. Usually, when we form the objective equation, it will consist of two independent variables. And in this case, they will be the radius and the height, as given by the relation V equals to pi r square h. The second equation we want to form is called the constraint equation, which represents the physical constraint. In this case, it will be the fixed amount of material. The use of this constraint equation is to provide a relationship between the two independent variables. So I can now say that h is a function of r by solving this constraint equation. And therefore, I can now substitute this constraint equation into the objective equation to eliminate the variable h such that v becomes a function of just r. Since it is now a single variable equation, we can now differentiate this single variable equation and equate it to 0 to solve for the stationary point. A stationary point is where the gradient is 0. It could be either a maximum point, a minimum point, or a point of inflection. Thus, we will need to check for the nature of the stationary point once we find it. The test for the nature will be covered in the next two pages. The first test for the nature of a stationary point is the second derivative test. It makes use of the sign of d2y over dx squared to determine whether a stationary point is a maximum or a minimum point. So what it does is d2y over dx squared is actually d over dx of dy over dx. That means the gradient of the gradient. If the second derivative is positive, then it corresponds to a minimum point, because if we have a minimum point, the gradient before the turning point will be negative, then 0, then positive. We can see that the gradient of this gradient is positive since the gradient is going to change from negative to positive, and thus it corresponds to a minimum point. Next, if d2y dx squared is less than 0, it will mean that it is a maximum point, because for a maximum point the gradient goes from positive to 0 to negative. That means the gradient of the gradient is negative. And finally, do note that if the second derivative is 0, it does not mean that the stationary point is a point of inflection. It is indeterminate, and we have to proceed to make use of the first derivative test to determine the nature. The first derivative test is a more robust test, as it can determine if a stationary point is a point of inflection. It makes use of the signs of dy dx at the stationary point, a point slightly smaller than the stationary value, and a point slightly larger than the stationary value to determine the nature. To use the first derivative test, we first construct a 3x4 table. In the first row, we will write down the three x values, which is the value that is slightly smaller than the stationary value, the stationary value and a value that is slightly larger than the stationary value. In the second row, we will write down the sign of dy dx at the corresponding points. In the third row, based on the sign of the gradients, we can sketch the rough shape of each one and thus deduce the shape of the stationary point. Over here, we can see that it will have a shape that looks like this. Therefore, we know that this is a maximum point. Subsequently, we can get the minimum and inflection points using this same technique by analyzing the shape of the three gradients. To get a minimum point here, inflection point here, and another inflection point over here. In example 1, we want to make a cylinder which has a fixed volume of 500 cm3. Only the volume is fixed, but I can play around with the radius and the height of the cylinder, all of which should give me the same volume of 500 cm3, but the amount of material used will be varying because the surface area of the cylinder is changing. So I want to find out the minimum cost of making the cylinder, which also means that I need to find out what is the minimum surface area. So first, let's identify the objective equation. Since I want to find out the least amount of cost, that means I need to form the function for the cost. This will be my objective equation. C equals to 0.10 multiplied by 2 pi r squared plus 2 pi r h, where 2 pi r squared is for the top and bottom surfaces of the cylinder, and 2 pi r h is for the curved surface area. Now we see that this cost function has two variables, r and h, and therefore we need to form the constraint equation to find out the link between these two. And we know that the constraint equation can be formed using the fixed volume. So we know that pi r squared h must be equal to 500, and I can rewrite this as h equals to 500 over pi r squared. Let me name this equation 1 and equation 2. Now I can substitute equation 2 into equation 1 to get C equals to 0.10 multiplied by 2 pi r squared plus 1000 over r. Now note that this new equation consists of only one variable r, which now I can differentiate. So the C over the r will be equals to 0.10 times 4 pi r minus 1000 over r squared. And for the stationary point, I need to solve for the C over the r equals to 0. And therefore, I get 4 pi r minus 1000 over r squared must be equals to 0. And this gives me r equals to cube root of 250 over pi cm. With this, I only know that this is a stationary value. I do not know the nature of this stationary point yet. And therefore, the next thing to do is for us to determine the nature of this stationary point. And I'm going to use the second order test, the 2c over the r squared. It will become 0.10 multiplied by 4 pi plus 1000 over 2000 over r cubed. And we can substitute r equals to cube root of 250 over pi in, and we can see that the 2c over the r square will be a positive term. Therefore, this tells us that r equals to cube root of 250 over pi gives us the minimum cost of making the cylinder. In solving optimization problems, two types of geometries are very frequently tested, and we need to be able to interpret them in order to obtain the constraint relation. The first is if we have a cylinder inscribed in a cone, where the top of the cylinder touches the inside of the cone, or if we have a rectangle inside a triangle. In both of these cases, we need to make use of similar triangles to form the constraint equation. So if we have these cases over here, we will have to look at this triangle versus this triangle. Likewise, for the 3D case, it will be this triangle versus this triangle. In the second geometry, we have a cylinder inscribed in a sphere or a rectangle inscribed in a circle. In this case, the constraint equation can be formed using Pythagoras theorem between the radius of the circle and the two half sides of the rectangles, like this. And the same thing over here, radius of the sphere with the two half sides. In example 2, we have this semicircle and there is a rectangle that is inscribed within. And we want to maximize the parameter of this rectangle. So let's say that the length of this rectangle is 2y. And if we look at this right angle triangle over here, it will be r, x, and y on its three sides. And this will form the constraint equation that we need later on. First, let's form the objective equation. P will be equals to 2x plus 4y. And next, we can form the constraint equation using r squared equals to x squared plus y squared. Or I can also rewrite it as y equals to square root r squared minus x squared. And with these two equations, I can substitute equation 2 into equation 1. And that gives me p equals to 2x plus 4 square root r squared minus x squared. Now this is a single variable equation which I can differentiate. dp over dx will be equals to 2 minus 4x over square root r squared minus x squared. And I need to equate this to 0 in order to solve for the stationary point. And if I solve this equation, eventually I will end up with x equals to 1 over square root 5r. Now with this value of x, we need to determine the nature of this stationary point. And I'm going to make use of the first order test because it will be very difficult for us to differentiate this expression and it will be very messy. So what I am doing is I am going to assume r is equals to 1 when I'm going to key in my calculator. Since r is just a random number, I can just substitute 1 when I key into the calculator to find the sign of dy dx. So I have this table over here. In the first row, I'm going to put in the three x values, 1 over square root 5r minus 1 over square root 5r and 1 over square root 5r plus. And next, I'm going to find out what are the signs of dy dx. If I just substitute 1 inside my calculator and also the value of x, I will get positive values here, 0 here, negative here, which corresponds to a shape like this. And therefore, I know that x equals to 1 over square root 5r gives maximum p. And therefore, the largest perimeter p will be equals to 2 1 over square root 5r plus 4 square root of r square minus 1 over square root 5r square. And if we evaluate everything out, we should get 2 square root 5r cm.